So with problem 1116 now, we are going to define and indicate the significance of Okazaki fragments, DNA ligase, and primer RNA during DNA replication. Okay, so let's take a look at those three things. I'm going to start by diagramming a replication fork. Okay, no, I don't like that. Here we go. So here's our replication fork, and I'm going to have the 5' end here, 3' here, 5'. Oh, I'm out of my little pad here is not big enough. Okay, here we go. 5', 3'. Okay, replication fork, and RNA. The RNA primer is going to be put down by primase, and it needs to occur one time down here, 5' and 3' direction, and over here now we're going to see these little RNA primers, all along this strand up here. Okay, so this is the lagging strand template. So the RNA primers will be all over the lagging strand template. And we really only need one on the leading strand template. So remember, the leading strand is synthesized continuously. So DNA polymerase 3 can come in here and it can synthesize this continuously because it is being extended in the 5' to 3' direction the same way. It's being extended in the same direction as the replication fork is moving. So the replication fork is moving in this direction. And keep in mind that, on the other, replication happens bidirectionally, and there's another replication fork on the other side of this one that we're not looking at. So we're just looking at one of the two replication forks that initiate from an origin of replication. Okay, so now these are the Okazaki fragments, right? So DNA polymerase 3 is going to fill in these little Okazaki fragments here. It's going to synthesize the Okazaki fragments. Okazaki fragments. There's one here. And the reason these have to be synthesized in fragments is because the replication fork is moving this way, but these polymerases only work in the 5' to 3' direction. Right, so here's the 5' to 3' direction for the lagging strand. It's going the opposite direction of the replication fork. So the replication fork is moving to the right here. This lagging strand is being synthesized towards the left. So those are Okazaki fragments. We need the RNA primers all along the lagging strand template in order to synthesize the Okazaki fragments. The lagging strand is synthesized through Okazaki fragments, and the leading strand is synthesized from one long continuous, as one long continuous fragment. So there's one more thing, the DNA ligase it wants us to look at. So DNA ligase comes in at this point up here. Let's take a look at just, let me see, one of these things right here. Okay, so we have the end of one Okazaki fragment right here and the beginning of another. So let's see if I can blow this up a little bit. Select, copy, paste. Let's see. I don't really like that. No, it doesn't look that great. So what can I do? Okay, so I think this will work. What I'm going to do is diagram this little section right here that I just pasted. I'm going to diagram this a little neater. So I'm going to show the lagging strand template right here. And this is the 5' end, and this is the 3' end, and this is just a section of the lagging strand template. And I'm going to diagram the end of one Okazaki fragment. So there's the end of one, which I'm showing right here. And I'm going to show the start of another. There's the RNA primer. And there's the DNA portion of this Okazaki fragment. So we have the end of one right here and the start of another. I'll put those in different colors. How about red for stop of one Okazaki fragment and the beginning of another, and the blue is the RNA. Okay, now this is where DNA polymerase 1 comes in, and what it will do, you know, we said DNA polymerase 1 has a 5' to 3' exonuclease activity, so it comes in, and keep in mind that we have 5' here and 3' here. So it comes in and it can chop out all of these RNA primers. So these primers are going, this RNA, it can chop out all of these ribonucleotides, I should say, of the RNA primer. So, and it can do so in this direction, the 5' to 3' direction. And as it's cutting those out with its exonuclease activity, it can add DNA nucleotides, right? It can add those to be complementary to these bases of the template right there. So what's going to happen? DNA polymerase 1 comes in here. Where's my eraser? I want the eraser here. I want to get rid of all of these, and it chops them out, gets rid of all these ribonucleotides of the RNA primer, and it doesn't use an eraser, of course, right? And it puts in the deoxyribonucleotides. But what can't it do? It can't join that last can't make that last phosphodiester bond. So as a result, we're going to have here is maybe a phosphate on the 5' end of this base, whatever this base is right here, and we're going to have a hydroxyl on the end of that base right there. So what we need is DNA ligase to come in. Okay, now DNA ligase comes in. DNA polymerase 1 is all done. DNA ligase comes in and fixes this. Well, we call this a nick. This is a nick in the DNA backbone. The backbone is the phosphodiester linkages between the carbon sugars. So this is a nick. We're going to fix that with a DNA ligase. It's just going to join this phosphate to that oxygen. Essentially, that's what it's going to do. Specifically, it may involve a couple more other things. But essentially, what it does is it joins that phosphate to that oxygen, fixes that nick, so there's no more nick anymore. Okay, so we now know what DNA ligase does. We know what the RNA primers are for. And we have reviewed what Okazaki fragments are. And that's the solution to problem 1116.